All right, 1.3.1. Today we are going to describe quantitative data with numbers. So taking a look at the objectives, got a few things. Some of this will be review. Some of it I expect to be brand new, but it's not too long of a lesson. So we're going to calculate measures of center, namely the mean and median. Calculate and interpret measures of spread, the range and the IQR. Choose the most appropriate measure of center and spread in a given setting, and identify outliers using the 1.5 IQR rule. Finally, we'll make and interpret box plots of quantitative data. All right. So the mean, this is what I would have expect you to already have some experience with. The mean is a measure of center. The notation we use in statistics is x with a bar over it, and it's pronounced x bar. So the mean of a set of observations, to calculate that, you're going to add their values and divide by the number of observations. So here we have our basic mean formula. And some more notation. In math, the Greek letter capital sigma is short for add them all up. So one way you'll see this formula written is like this. You do get a big formula packet for AP statistics that you use on the exam, and so it'll have this formula in it. You just have to get used to some of the new notations. So just remember that sigma means add them up. X sub I means all individual data, and then N is the number of data. Okay. Oh, one other thing I wanted to mention is that the mean is what we call a measure of center. So measures of center are what we would consider like a typical value for the data set. So we try and use them as representative of where most of the data in a data set is, or I shouldn't say most of, where the data set is centered. And so one way to do that is find the mean. Colloquially, you probably have heard the mean called the average, which is fine, except that can sometimes cause confusion because media will also use average sometimes to talk about the median. So the median is the true midpoint of a distribution. It's the number such that half of the observations are smaller and the other half are larger. So to find the median of a distribution, you're going to arrange all observations in order from smallest to largest. If the number of observation is odd, the median is the middle number in that list. If it's even, the median is the average of the two center observations. And when I say average in that case, I'm referring to the mean of the two centered. So if I gave you, let's just do quick off-the-cuff example. So if we had a data set that was like 1, 1, 2, 4, 5. The number of data in that data set is 5. I've already ordered it, so the median is the middle number. All right, let's do another similar data set. 1, 1, 2, 3, 4, 5. Now the number of data in my data set is 6, so the median is going to be the average of those two. There we go. Okay, resistant measures can resist the influence of extreme observations, e.g. outliers. So let's go back to this. Let's change up these data sets and let's throw in some extreme outliers. These are all pretty small numbers, pretty close. They're all single digit positive numbers. So what if I threw in a huge number and I made, instead of 5, this data set, the upper value is 1,000. Does that change the median? Nope, these are still in order. The median would still be the average of the two middle. The median would still be 2.5. So even an extreme observation doesn't mess with the median. And so in this case, the median is what we call a resistant measure of center. Okay? It's resistant to extreme observations. Let's look at the mean. I'll do a little off-the-cuff example here. Let's say we have 1, 1, 1, 1, 1. My data size is 5. And if I were to find the mean of this, x bar would just be 1 plus 1 plus 1 plus 1 plus 1 plus 1 divided by 5, which is 5 over 5, which is 1. Okay, now let's make this a little bit more of an extreme situation. Instead of 1, let's make our last one 100. And recompute the mean. So now it's going to be 1 plus 1 plus 1 plus 1 plus 100, which is actually going to come out to 104 divided by 5, which changes the mean completely. 104 divided by 5 is 20.8. So the mean is not a resistant measure of center. Which just means that it's severely impacted by any outliers or extreme data values that deviate extremely from the overall pattern. So just to summarize that, mean, not resistant, median, yes, resistant. Okay, so now we'll talk about a few other measures, quartiles and the IQR. To calculate quartiles, you'll arrange the observations in increasing order and locate the median. The first quartile, which we'll call Q1, is going to be the median of the observations on the lower half. So basically, you've broken your data set up into two halves. And on the lower half, if you treat that as its own data set now, if you find the median of that, we call that Q1. Then if you find the median of the upper half, that's Q3. The interquartile range, the IQR, is defined as Q3 minus Q1. The IQR is what we call a measure of spread. So it measures how spread out the data set is. And it is resistant. Because you're taking only the median of the lower half and the median of the upper half, you're leaving out kind of any extreme observations, any outliers. And so it gives you a general idea about how spread out your data set is without including any outliers. So it is a resistant measure of spread. We'll do a couple examples where we find the IQR. All right, the 1.5 times IQR rule for outliers. So call an observation an outlier if it falls more than 1.5 IQR above the third quartile or below the first quartile. So to get the lower bound you're going to take whatever your value for Q1 is, you're going to subtract 1.5 times the IQR. And if you have any data that falls below that, you'll consider that data a possible outlier. The upper boundary for outliers, you're going to take Q3 and you're going to add 1.5 times the IQR. And any data that falls above that we'll consider a possible upper outlier. And again, right now I'm just giving you the definitions. We'll do examples of these. Okay, the 5-number summary of a distribution is the minimum value in the data set, Q1, the median, Q3, and the maximum value. And that's actually how you make a box plot. So you guys have seen box plots before, but you plot the minimum, or I would have expected you to have seen them, maybe you haven't. On a horizontal axis, you plot these 5 points. You put a box connecting Q1 and Q3. You put a line through the median, and then you put whiskers connecting the minimum to Q1 and the maximum to Q3. And this gives you a visual of the spread of the 4 quartiles of the distribution. Within each quartile, you will have the same amount of data. It'll be 25% of your data. So no matter how big or small each section is, each quartile still represents a quarter of the data. And so if it's small, that just means that within that quartile, the data is closely grouped together. If it's really stretched out, that means the data is distributed much more widely over that quartile. Okay, and so this is just a bullet point, how to make a box plot. I just kind of went over that. Yeah, if you do have outliers, we won't connect the whisker from Q3 to that or the whisker from Q1 to the outlier if depending on if it's a high or low outlier. Instead, what you'll do is mark those with an asterisk, and then you would connect your whiskers to the next highest and or lowest point that is not an outlier. I'll show you what I mean by that. All right. Here's some data for McDonald's fish and chicken sandwiches, and it's the amount of fat in grams in 9 different sandwiches, along with a stem plot. And the first, for part A, we want to find the mean amount of fat for the fish and chicken sandwiches. So we could do this by hand, and by hand I mean we could throw those numbers in the calculator and divide by 9. So add them together and divide by 9. However, I'm going to show you some functions of your calculator to make you a little bit more efficient at dealing with stuff like this. Okay, so the first thing we want to do is throw this data in our calculator. So I'm going to go to my calculator. We're going to first go to Stat, Edit. If there is anything in List 1, make sure you scroll up to highlight the name of List 1, hit Clear, then scroll back down and it'll clear out the whole list. Don't hit Delete. That will delete the list. As you can see, I just did there. If you do hit Delete, just go back to Stat, click Setup Editor, hit Enter, and then when you go back into your list, it'll be reinstated there. All right, okay, so I'm going to enter the data for the fat in the chicken and fish sandwiches at McDonald's. Good. And we note that we can see here that I'm on cell 9 and there were 9 pieces of data. There were 9 sandwiches, so that's good. All right. So the next thing I'm going to do is quit to the main menu. So I'm going to hit second quit, just in my main calculation area. I'm going to go back into Stat. I'm going to scroll over to calc, and the first option is one variable stats. If you have a newer calculator like I do, it'll ask you what list you want to find one variable stats on. If you have an older calculator, it will just take you, here, hold on, I'll show you what it'll take you to. Let me clear that out. It'll just take you here, and you need to enter right here which list you want it to calculate the one variable stats on. It'll default to list 1. And in this case, that is where we put our data. So then I can hit enter, and I'm given a whole bunch of information. So I'm going to take us back to the original screen, but you can see the first thing up here is X bar. So that's our mean. So 19.9 grams is our average. So we'll go ahead and write that down for A. Say, whoops. X bar equals 19.9 grams. Then for B, they say the Premium Crispy Chicken Club is a potential outlier. How much does this sandwich increase the mean? So first I want to see how we find that it's a potential outlier. So I'm going to take us back, and that is this one, the 33 grams. So remember that that would be considered maybe a potential upper outlier. To find the upper boundary for potential outliers, we do Q3 plus 1.5 times the IQR. Well, I can get all that information from my calculator. All right, so if I scroll down, you can see we're given Q1, the median, Q3, the max. We're actually given the entire 5-number summary right here. So my Q3 is 24.5. And then remember, to find the IQR, you do Q3 minus Q1. So that's going to be 24.5 minus Q1 is 15, so minus 15. Okay, so taking you back to our slides, here's the calculation I would make to find the upper boundary for possible high outliers. All right, so I'm just going to pop that in the calculator. So the upper boundary is 38.75. So by our possible outliers rule, this would not be considered an outlier. But we still need to answer their question, which is how much does this one sandwich increase the mean? So to do that, let's go back to our calculator. Let's go back to our data set, so stat edit. Remember that our mean was 19.9 grams with that data value included. I can just delete that one data value and recalculate. So stat calc one variable stats. And I get a mean of 18.25 without it. All right, so I was just making a note. I said the mean is 18.25 grams without the PCCS, Premium Crispy Chicken Club Sandwich. So it increases the mean by approximately what is that, 1.65 grams. And I just subtracted the mean with that sandwich to the mean without that sandwich. All right, so now we're given some data set on the fat content for their beef sandwiches, also called hamburgers by any normal person. And I want to compute whether or not there are any outliers. So we're going to find both the upper and lower bound for that. So first thing I want us to do is go ahead and enter that data into list 1. Again, I can clear this out. All right, so 9, 12, 19, 23, 24, 26, 26, 27, 29, 29, 31, 43. All right, we'll go ahead and quit to the main screen. I want to go to Stat, Calc, One Variable Stats. I entered that data into list 1, so I want list 1 there. All right, and they specifically are just asking us about whether there are outliers. So we're going to use our 1.5 IQR rule. So I'm going to scroll down here so I can see the 5-number summary. I'm going to quickly make a note of that 5-number summary for myself. So that's 9, 21, 26, 29, 43. All right. And so let's get to calculating our lower boundary. Which is going to be Q1 minus 1.5 times the IQR. All right, so Q1 is 21 minus 1.5 times the IQR is going to be 29 minus 21, Q3 minus Q1. Okay. All right, so our lower boundary for outliers is 9. Our upper boundary is Q3 plus 1.5 times the IQR. So Q3 is 29 plus 1.5 times 8. Is 41. All right, so now we need to decide, do we have any lower or upper outliers? So there's kind of controversy. Some people interpret the boundary as like the limit, meaning if you have a data value at that limit, you should consider it an outlier. Some people consider it a physical boundary, so it's like, nope, if anything is below or above those boundaries, then those are considered outliers. The truth is, this isn't a hard and fast rule. This is a rule of thumb. The person who invented the 1.5 times the IQR rule for determining outliers was asked why 1.5 times the IQR. And his answer was 1 didn't seem like enough and 2 seemed like too much. So this isn't a hard science here. This was a rule of thumb. And outliers are really just deviations for the overall pattern that need to be further investigated. So it's a little bit up to the statistician to decide, am I going to include this as a possible outlier or not? For you, to give you guys something concrete, let's just treat them as boundaries, meaning data has to fall above or below the boundary to be considered an outlier. Meaning, we have a 9 in our data set. Do we consider it a low outlier? No, because 9 is our boundary. But our upper boundary is 41. We have a sandwich that has 43 grams of fat, so 43 would be considered an upper outlier. All right, so let's do one more. We'll make a box plot for this data. I'm going to talk about how to use your calculator to do this. I used to have my students do their first one by hand. I don't know that that is a relevant use of time. So I'm just going to show you how to do it in your calculator and what you need to copy down and label to receive full credit. Because you will have to make box plots. You can do it in your calculator. You just need to be able to copy down the appropriate amount of detail and label it appropriately. So let's go ahead and do that for this last in-class example. And then I'll get you to your student example. Okay, so this is the number of home runs that Hank Aaron hit in each of his 23 seasons, and we just want to make a box plot for this data. So first thing we'll do is go to our calculator, open up Stat Edit, clear out anything that is in there, and enter our 23 pieces of home run data. So we should have 23 entries when we're done. All right, and I can verify that the last one is on cell 23, so I should be good. All right, so how do you get your calculator to make a box plot for you? First thing, go into y equals. If there's anything in there, let's turn off or clear it out. We don't want any algebraic graphs graphing over our box plot. Next thing, we're going to go into stat plot, which is second y equals. I have plot 1 on right now because the last thing we were doing was making histograms, but now we want to choose a box plot. There are 2 box plots to choose from. Both of these are box plots. The one with little dots by it will include any outliers as points instead of connecting them with whiskers. So it'll use the 1.5 IQR rule. So we want to choose this one just in case there are any outliers. They'll be shown as points outside the whiskers. And then again, you get to get creative and feel free to be yourself. Choose your mark and your color if you have a fancy calculator. Then we're going to quit to the main screen. So next thing we're going to do is go choose a window. We're going to go to the zoom and choose the 9th option, which is zoom stat. And this will give us a good window for our box plot. Oh no, what did I do wrong? Did I not turn it on? Huh. That was weird. Anyway, there's my box plot. All right, so now when you want to sketch it over, here's what we need to do. If you hit the trace button, it'll let you jump around between your quartiles. So my minimum is 10 home runs. Q1 is 26, the median is 34, Q3 is 44, and the max was 47. And so I just want to sketch that on an x-axis. We're going to label the x-axis, and you're going to scale the x-axis. So give me 1 second. Okay, so this is all I did. I gave a horizontal axis. I gave some scaling. All I did was write down the 5-number summary. So I just marked where the minimum, Q1, median, Q3, and the max were on the x-axis. I did label what those numbers represent. These are home runs per season. And then I drew my box plot, right? So a box around Q1 and Q3, a line through the median, and connected the max and min using whiskers. So no outliers. There were no values that breached the 1.5 IQR boundary. But what I want to make clear is what we're seeing here is a visualization. This is a graph that has a clear left skew. You can see it stretches towards the left, but every quadrant contains 25% of the data. So that's 25% of the data. This is also 25% of the data. So it's much more compact on the high end, right? On that last quartile, that contains a quarter of the data, meaning he had just as many seasons up here at 44 to 47 as he did from 10 to 26 home runs per season. And then the other two, these are each 25% of the data as well. So a box plot just gives you an idea of center using the median specifically, and spread. The IQR is the box, but you're also able to see the overall range, right, by the length of the entire graph. So it's just a really concise way of kind of visualizing a distribution. All right, so for this one, this is your student example. I just real quick wanted to talk about it, and it is a survey of study habits and attitudes for 18 first-year college women and 20 first-year college men. And what I want you to do is you're going to put each one in a different list. So put the women in list 1 and the men in list 2, and you can turn on 2 box plots. It's called parallel box plots at the same time. So you can compare those distributions to each other on the same x-axis, and then use that to answer the question if you think these data support the belief that men and women differ in their study habits and attitudes toward learning. And they say that high scores indicate good study habits and attitudes towards learning. Don't worry about what it means to follow the 4-step process. I can explain that later. It's just this textbook's way of getting you to organize your thoughts and make sure that you're fully answering a statistical question with enough detail that you would receive full credit on the AP exam. But we'll talk about that a little bit later. But give that a try. Try and get those parallel box plots graphed in your calculator, and we'll talk about this next class.